Hey guys, just got this battery in for review. It's a 51.2 volt, 100 amp hour lithium iron phosphate battery from WEIZE. It's a very basic battery that sells for cheap, so it may be a good buy if it tests out well. In this video, we're going to do a full review of this battery. We'll take a look at the external characteristics, some of the specifications. We'll do some capacity testing, and then we'll tear it down to see how it's built inside. This battery is 20.5 inches in width, 8.6 inches in height, and 9.4 inches in depth. It has a nominal voltage of 51.2, capacity of 100 amp hours. It has a max charge current of 100 amps, recommended to charge at 20 amps, a continuous discharge of 100 amps, and a peak discharge of 200 amps for up to 3 seconds. These are all very standard specifications for a lithium iron phosphate battery. It comes in a very standard plastic case like we've seen with many of these batteries. We have our terminals, our positive and our negative. These are M8 bolts. We have carry handles on both sides, though honestly with the weight of this battery, I feel a little better picking it up by the bottom. And then we have a large warning here for parallel and series connections. You can wire this in parallel obviously, but you cannot connect this battery in series as with most 48 volt batteries. The manual that comes with it is all very basic information. We have these specifications, most of which we've touched on already, but one thing that did catch my attention in particular is that this battery is rated for 2,000 cycles at a 100% depth of discharge. I would expect to see double that for most lithium iron phosphate batteries. We have a very detailed list of the BMS specifications. This is nice to have on hand. Most battery manufacturers don't include BMS specifications to this level of detail. So here we have a graph of the discharge cycle life, and you can see at a 100% depth of discharge, it's only rated for 2,000 cycles. Now this is really the minimum, so you could see more than 2,000, but... And lastly, we have some warnings and troubleshooting information. Alright, so we're hooked up to my standard capacity testing setup here. I charged this battery using an Ames lithium iron phosphate rated charger. And you can see we're sitting around 55.20 volts. It's been floating like this for about a day and a half now, so it's had a little bit of time to balance. And my test load will be the space heater on low. It should pull approximately 980 watts. So here we go. All right, we'll leave this run until the BMS in the battery stops the test, and we'll see what our measured capacity is. All right, and our discharge test did shut down here. It looks like the BMS in the battery stopped, and we're only at 90.9 amp hours. That doesn't sound right. I certainly expected this to perform at full capacity, and it did look like the voltage was a little bit low when we started the test, so I'm gonna guess maybe those cells are not balanced. Now obviously that test did not perform as well as I was expecting. We're missing 9 to 10% of the battery capacity. Now that Ames charger per the manual on the lithium iron phosphate section has a max voltage of 57.6 volts. So it's not quite up to the full 58.8 volts that gives you the 3.65 volts per battery. However, this battery is also rated at a charge voltage of 57.6 volts. And I test all of my batteries to the same standards using the Ames chargers. So the plan's going to be to disassemble this battery, do the internal stuff. The missing capacity is most likely from the cells not being balanced, so we'll balance the cells, put it back on the capacity tester, and then see if we get any better results. Safety glasses, hammer, and reminder never to do this at home. All right, that's our battery pack down in there, but the first thing I noticed is, man, these wires are thin for a 100 amp continuous rating. We have a number 6 silicone insulated wire here for the positive, but the negative is a pair of number 10s, and those are just thin wires. Like, I get it's a 200 degrees Celsius insulation rating, so they're made to get warm, but so what do we have here? It looks like we have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 cells across the top, 8 cells across the bottom, and the bottoms are pushed together here. So the terminals are here and the terminals are here. We've got our main positive, our main negative conductor, and then we have this short conductor jumping the 2 packs together. And look at how that terminal is bent down in there. And this one too, really, look at that. Now they do have some of this epoxy board just to cushion that terminal from pressing into the cell, but man, that just does not look good to me. But the balance leads, while they are a spaghetti nest here, they are taped down nicely to prevent movement. And we've got a series of straps holding these batteries together. We've got 2 per battery pack. So I was pulling on this strap here trying to get this battery to come out, and I really didn't even use much force and it just snapped. So I have to question now the holding strength of these straps. See, it just snaps and I've hardly pulled on it. I don't know guys. It's not looking good so far. Yep. All right, so as you can see here, I did manage to get the battery extracted. It was not easy, and you can see how we've got terminals on one side, and because the batteries are butted up against the bottoms, we have terminals on the other side. I don't really like that particular design. It's difficult to know which way to work with the battery because if I stand one side up, the other side is down against the table. Additionally, in its normal operating orientation, as you see set here, it means the batteries are sitting on their sides. And while some manufacturers do allow that orientation, others do not. So I've now stood up the battery so I can take a look at the terminals, which means 8 of the cells are now upside down, and that's definitely a big no-no from every cell pretty much that I've seen. So for those of you who ask which directions you can operate this battery in, it's pretty much only in the upright direction as you see here. Here we can see the aluminum bus bars. They are laser welded down to the terminals of the cells. The laser welds are nicely done. The bus bars appear to be of adequate size. It does look like they are upside down from what I can tell. These humps in the middle are typically to allow for expansion, and usually they're pointed upward. I guess there's no reason they have to be installed pointed upward. This is just the first time I've seen them installed pointed downward. But you can see we've got a piece of fish paper here, or battery paper, covering the tops of the cells. It is adhesive. Some of the wires are stuck down, some of them are not. These are the balance leads. I couldn't really tell you how the balance leads are affixed to the bus bars because they're upside down. So I guess that tells you which way the bus bar is meant to go if the lead and the ring terminal are on the opposite side. These balance leads are actually soldered onto a little tab, presumably a piece of nickel, which I think is then either laser welded or spot welded onto this aluminum bus bar. So that's why they're sort of flopping around there. There's no heat shrink, there's no ring terminal, it's just soldered onto that tab. They are held in place here for the most part. I don't know that I could really say they're routed nicely like I typically do. It's kind of just held with a piece of tape here. One other thing that did catch my attention here is on the BMS, we have the main negative coming off of the battery, but the way this cable is routed, you can see the cable's flattened a little bit there, and it's actually being pressed into the metal heatsink of the BMS. And that's definitely something that will be a future point of failure if this battery is operated in a vibration type environment, like in a vehicle, an RV, or something of that nature. Now, these terminals are very soft, which I guess is why they're bent inward like that. And the way they are bent, it looks like the bending has occurred from, you know, when that screw is being tightened down here, just the way this terminal is bent. And I can show you how soft they are here by, unbending it. I guess it was actually stuck down a little bit because it popped. I'm not sure what that was. Let's see if we can figure out what brand cells these are. Let's pull this off here. Here's a close-up of the QR code. It is not one that I personally recognize, and I did stick it in the Global Power QR code decoder, and it couldn't find any information either. So I'm not really sure what brand cells these are. I can just tell you it's not a widely recognized brand, at least based on lack of identification of the QR code. Taking a look at our BMS here. It is Topac or Topac SH. And we can see it has a rating of 100 amps. I see it stamped there twice. I don't read Chinese, but we can assume one of those is charge and one is discharge. There's not a whole lot to see on it here. It's on a piece of epoxy board with some adhesive foam there. We can see all of our balance leads coming in here. While they are a bit messy, this is good quality wire that they're using for the BMS leads. And we also have a single temperature sensor here, which was affixed to the, what would have been the side of the battery, but it's actually the top of the battery. You can see where it was stuck on right there. So I think that's just about all there is to see within the battery pack itself here. All right, so now we are charging at 5.7 amps. I'm gonna take the temperature sensor here and spray it with some of this computer duster and just see if we can trigger any low temperature charging protection. Oh, it actually worked. I don't even remember if this battery was advertised as having low temperature protection. Let's warm it back up here and just make sure it starts charging again. There it goes. So this battery does have low temperature charging protection. That's pretty cool. Alright guys, so I charged this battery up using the Ames charger until the charger shut off again. Then I took my iCharger X6 here and I put it on the cells in groups of 4 and charged them up with normal balance mode to 3.65 volts. This battery should be entirely charged and balanced at this point. And the most that went in was 0.7 or so amp hours. It was nowhere near the 9.5 or so amp hours that was missing. So this is as close to full charge and balance as we're going to get. We're going to run the capacity test one more time. We'll see what the resulting capacity is, and then I'll stick my voltmeter on once it's done and see what the lower end balancing looks like. So here we go. And test number 2, here we go. $102.64 amp hours on the second test. Alright, so there you go guys, 102 amp hours on the second test. I have a little bit of difficulty believing that the balancing I did made that much of a difference. I mean, that gave us an extra, what was that, 11 amp hours over the first test. Now, this first cell here is the weakest cell. You know, once it got down to around 2.5 or 2.6 volts, it did start dropping very quickly. And the low voltage disconnect of this BMS is around 2.3 volts. And I did see it drop down to about 2.2 volts before it actually shut off. That's what this multimeter was watching when you saw it shut off there, is I went and found the lowest cell and I put my fluke meter on there to see what it was actually reading. I suppose we could say it did pass the capacity test, but I can't just throw out that first result. I can't just say, I don't like that first result, so I'm going to throw it out and use the second result. I think maybe they need to do a little bit better job of balancing this before they send it out to the customer. Obviously, if you purchase one of these, you're not going to be taking it apart and balancing out cells like this, so you may have to cycle it several times. So all that being said, this battery is cheap. It sells for around $970 on their website, and clearly they have cut some corners to make it cheap. I suspect these are lower quality cells considering they're only rated for 2,000 cycles at a 100% depth of discharge. We should see a little bit more from lithium iron phosphate batteries. I couldn't identify what brand they are, what model they are. Just the way the balancing leads are run. I don't like the way the pack is assembled in the case with the two ends butted together like that, so that the cells are on their sides, having terminals face in both directions. But yeah, I'll leave that up to you guys. Please let me know what you think. Questions or comments, anything you want to see more of. Hit that like button before you go, and thanks for watching.